so much.
Good evening, everyone. Veer Maheshwar Charitable Trust Latur MS India organizing daily international webinar series. In this series, we invite speakers from India and abroad. The speakers are sharing their knowledge as per their field of study and research. Education, law, technology, environment, health, all topics are accepted here. Speakers are invited from India and abroad, and it's running from last 12 years. If you see join the speakers, they are mostly women resource persons. So that this is a women empowerment series mission. Till now, we have completed more than 1,400 daily international webinar series, and it is running from COVID period. So today we welcome our today's speaker. We have invited her, Leili Esrafil ma'am, who
Yes,
is
Leili
from
Esrafil.
University of Antwerp. Yeah, sorry, and she's from Belgium, Belgium, and her topic is HBD MOFs as a organocatalyst. So today we welcome her, and we first of all thank you for her for joining here. She holds PhD in chemistry and applied engineering. She is expertise across organic chemistry synthesis, solid state and super molecular chemistry, and advanced analytical characterization. Her synthesis of her background, research background spans the design and synthesis of functionalized organic links and micromolecules, and the development of 3D metal organic framework MOFs, and the study of solvent and structure dependent application of them in catalyst sensing. So she is a FWO postdoctoral fellow, and her current work focuses on hydrogen bond donating MOFs as a organocatalyst. And she is an extensive and hands-on experience of characterization in solid transformations, and supported by advanced techniques such as SCXRD, PXRD, FTIR, NMR, UV visible, TGA, DSC, and etc. Beyond her academic work, she tries in multidisciplinary setting, and she is motivated by roles that blend practical laboratory work with process insight and data-driven decision making. She is particularly interested in applying her expertise to chemical process development and optimization. And she has invited from so many organizations for delivering her academic talk. And today we are very fortunate that we are eager to listen her speech from her. We welcome you from my organization and from all participants. I invite you to deliver your speech. Thank you.
Thank you so much for this, for your attention also for this organization. Thank you so much. Hello, everyone. My name is Leili Esrafili, or everyone calls me Lili, and I am currently a postdoc researcher at the University of Antwerp. I hold a double PhD degree in chemistry and applied engineering, and my research focus is on metal organic frameworks, or MOFs, particularly mesoporous MOFs with and also MOFs functionalized with hydrogen bond donating groups. Today, I am fortunate that I am here and I will presenting my work on hydrogen bond donating MOFs as an organocatalyst. The main idea behind this research is simple but powerful, and we basically want to answer this question that can we embed molecular catalytic functionality inside a highly ordered porous frameworks to achieve better activity, selectivity, and stability. Before discussing on MOF, I want to briefly introduce the conceptual foundation of this work, supramolecular chemistry. Supramolecular chemistry is often described as a chemistry beyond the molecule, a term introduced by a Nobel Prize winner John Marilyn, and it is interested of focusing on covalent, instead of focusing on covalent bonds, this field studies how molecular organization happens through non-covalent interactions, such as hydrogen bond, pi-pi interactions, electrostatic forces, or van der Waals interaction. These peak interactions allows molecule to assemble into larger functional groups, functional systems, and has two major concepts. One is self-assembly, and the other is host-guest chemistry. Self-assembly is spontaneous and reversible organization of a molecular building block into ordered structure. Nature relies heavily on this principle, for example, in protein foldings and DNA base pairings. And the other one, as I said, it's host-guest chemistry. Here, one molecule, the host, provides a defined environment that selectively binds other molecules that we call guests. And normally, host molecules is bigger than the guest molecules. And this concept also known as a lock key in chemistry. Moving one step further, we arrive at coordination polymers. Coordination polymers, these materials are constructed from two key components, metal nodes and organic linkers. Metal nodes acting as a node or a connector between these organic linkers. The final geometry of the coordination polymers depends on several parameters, metal coordination number, and also ligand density and flexibility and geometry. So when these components connect repeatedly, they form infinite networks that can extend it to 1 dimension, 2 dimensions, and 3 dimensions. Different combination of metal and ligand produces diverse structure motifs. In 1D system, we observe chain such as linear or zigzag arrangement. In 2D materials, networks like honeycomb or square lattice appear, and in 3D system, complex architectures like diamondoid or octahedron frameworks emerge. These structural diversity is important because structure diversity determines the function, especially porosity and accessibility of active site. But an important subclass of coordination polymers is metal organic frameworks, or MOFs. MOFs are crystalline porous materials composed of metal ions or clusters and connected with these organic linkers. Unlike many coordination polymers, MOFs possess permanent porosity. So in order to be established and be categorized as a MOF, it should be, first of all, connected by coordination powers, coordination forces, and also it should be permanently porous. Early MOFs mainly used oxygen donor ligands, such as carboxylate group, but later development introduced nitrogen bonds and multifunctional linkers. What makes MOFs exceptional is their extremely high surface area, sometimes exceeding 8,000 square meter per gram, making them among the most porous materials ever synthesized or even existed. Over the two decades, MOFs have emerged as an alternative to the traditional porous materials such as zeolites, mesoporous silicates, and activated carbon. To better visualize this number or put this number in perspective, if you take just 1 spoon of, let's say, MOF 5, and make it fine powder, the total internal surface area of this 1 spoon can be comparable to the area of an American football field. Additionally, MOFs offer thermal stability, which is mostly in zirconium-based MOF. Their structure is tunable. You can increase the length of linker. You can and by not changing the rest of functional group on the MOF, especially metal, you can increase the surface area, or you can add different functionality in the linker. As you can see here, these are series of other isoreticular MOFs or IR MOF that just they have the same topology, but the only difference is they have different surface area because their linkers are basically different. They have adjustable topology, as I said, and also they have different chemical tailorability, and this can happen via synthesis and after synthesis via post-synthetic modifications. The extremely large internal surface area of MOF provides abundant active sites and adsorption capacity and makes them interesting building blocks in application in gas storage or separation, such as hydrogen storage, carbon dioxide capture, and selective gas purification. And also other application like drug delivery, chemical sensing, energy storage, water purification, and environmental redemption, and this list goes on. Their precisely controllable pore environment allows molecular recognition based on size, shape, and chemical functionality. In addition, MOFs have emerged as a promising material for heterogeneous catalysis, where catalytic site can be incorporated directly into the framework or not, introduced later through post-synthetic modification, which is the focus of my research. And I want to start this catalytic activity and my research with the introducing of urea MOFs, or hydrogen bond donating MOFs. So urea groups, urea as one of the hydrogen bond donating moiety, you can have like thiourea, squaramide, and so on. Urea group are powerful hydrogen bond donors. Each urea unit can donate two parallel hydrogen bond to electron-rich species such as oxoanions or nitro groups, forming, as you can see here, a stable 8-member ring. In organocatalysis, this interaction activates substrate by increasing electrophilicity, essentially making a reaction occurs faster by lowering the energy barrier. However, sometimes this is a major problem too. Urea molecules tend to hydrogen bond with each other, as you can see here, and this leads to aggregation and self-quenching, which reduces catalytic activity, catalytic efficiency. So our strategy is to minimize this self-assembly. How? By immobilizing urea group inside rigid frameworks. By incorporating hydrogen bond donors into MOFs, active sites become spatially, as you can see, spatially isolated. And self-assembly between urea units now can be prevented, and catalytic site remains active. The porous structure now can act as a pre-organized reaction environment similar to enzyme active site, and they are really small nano reactors that can have also the active site inside them to propagate the reaction. The first example of urea-based MOF was reported by the Northwestern University group, especially by Omar Farha and Joseph Hopp. They synthesized NU601 and used it as a catalyst for Friedel-Crafts reaction between between pyrrols and nitroalkenes. The MOF showed higher catalytic activity compared to free linkers. However, stability was a major limitation in this work. The structure collapsed after removing solvent molecules, which here was DMF, because DMF itself has a amide group and can strongly interact with the urea, and this made urea group less active because it was directly in competition with the solvent molecule. In the second attempt, the same group used a more stable zirconium-based scaffold, which is UIO 67. They incorporated a squaramide hydrogen bond donor, which is stronger and more directional than urea, and they incorporated it via post-synthetic modification. This means they had this framework of UIO 67 from the beginning. They know that it is stable, and they add squaramide functionality after synthesizing this MOF to the structure. This modification drastically improved the catalytic activity in the Friedel-Crafts reaction of indoles and beta-nitrostyrene, as you can see here. The catalytic activity of MOF compared to isolated linkers drastically is better. This study clearly showed that combining robust metal nodes with hydrogen bond donating moiety is a promising strategy. But despite all the progress, there are other works, of course, on the literature. But despite all the progress, there were important limitations. For example, difficulty in creating mesoporous MOF with a large pore and surface area, which is really necessary for the catalytic diffusion, and stability challenges still when you using highly polar functional group, like when you add urea, thiourea, or squaramide. And third, high synthetic cost of many of these reported systems. I want you to note that hydrogen bond donors, like when you have urea, thiourea, or squaramide in your linker and you want to synthesize MOF, it is really challenging because these groups tend to involve an internal interaction during synthesis, and this makes the predictable structure really difficult, and sometimes you end up with a structure you don't want. To address this issue, we designed new MOFs containing both urea and squaramide functionality. Our design goal were larger pore size, high surface area, structural stability, and accessible catalytic sites. The resulting structure formed a large hexagonal and a square channel, and one of the MOF consists of zirconium zinc cluster, forming a stable architecture while maintaining accessible hydrogen bond environment. And inside each these hexagonal pores, which by the way they are almost 3 nanometers, you can have they have 12 hydrogen from 6 separate urea group that are facing inside the pore, inside the channel. We evaluated these MOFs as a catalyst for Friedel-Crafts reaction compared with the isolated molecular linker. The MOF showed significantly enhanced activity. These are the, sorry, where is my mouse? Yeah. These are the diagram for MOF, and these are for the isolated linker. As you can see, the catalytic activity improved significantly. This improvement rises from substrate pre-organization inside pores, cooperative hydrogen bonding, confinement effect, and improved reactant diffusion because of the larger surface area. The framework essentially behaves like a hydrogen enzyme mimics. But I want to also quickly take a look at the catalytic mechanism here, what happens mechanistically inside the molecule. So these are one of the linkers coming from this large pore. As you can see, it consists of hydrogen bond. Beta-nitrostyrene enters the pore and interacts with the hydrogen bond donor site. And as you can see, 2-point hydrogen bonding activates the nitric group. Electron density shifts and increases the electrophilicity of the carbon, alpha carbon, and indole attacks via reactive C3 position, and product formation occurs, and then after that the catalyst is regenerated. The MOF stabilizes the transition state and lowers the activation barrier and remains stable afterwards. To conclude, this work demonstrates how concept from supramolecular chemistry can be translated into solid state material through metal organic frameworks design, and by incorporating hydrogen bond donor functionality such as urea, thiourea, and squaramide into MOFs, we create organized catalytic environment where active sites remain spatially separated, preventing self-assembly effect and self-quenching effect, and which is commonly observed in the traditional system and molecular system. More broadly, this approach shows how MOFs can act as an enzyme-like platform where structure, functionality, and reactivity are precisely controlled. Looking forward, this system open opportunity for asymmetric catalysis, multi-steps reaction, and more sustainable hydrogenous catalytic processes. Thank you so much for your attention, and I'll be happy to take questions.
Thank you, Leili ma'am. With your studious talk, your characterization, and the detailed study of your research we have listened is very useful in the scientific field, and you have selected the topic as per your research. I am requesting all the participants, those who are here, they can discuss with our today's speaker.
Yeah. Uh, yeah, the benefits of organocatalysts relies on the effect of using them in future in our body. Everyone knows that in industry, definitely metal catalyst works better. Why we should move to organic catalyst? Why is the need for organic catalyst? But the question is, if we can use these metal as artificial enzymes future in our body, definitely no, they are so toxic for our body. So that is importance of organic catalysts. Another advantage of them is possibility of using them as the asymmetric catalyst. As you know, sometimes using metal doesn't allow us to choose the enantiomeric enantiomeric what is it? combination of final product. But if you have an organocatalyst that is left-handed or right-handed, you can design it in a way that gives you the result you want. So I can say it's two reasons. One, studies in the future to make them as a artificial enzymes, especially in future, maybe if we go further, making body parts maybe with them. And second, asymmetric catalysis.
Yeah, a very bright future of this research is there for the human progress and for the human body. So thank you for our participant, Dr. Swanand Shukla, sir, willing to ask. Sir, please.
We are discussing about the metal organic, the elements which we are using it as a catalyst, and you say that it is playing a wonderful role in the enzyme development in the body. But is there any toxicity of such kind of substances when we will be introducing it in the body, human body? That is my first question. And second question is, I have heard about some bio fuel, we can develop with this kind of catalyst. So whether it is a right phenomena or I got some wrong information. Thank you.
Thank you so much. Yes, that is also a concern. That's why I used zinc here. It depends on what you want to use. We definitely have biomorphs that you can use in the body without having a toxic effect. Depends on the linkers and metals you're using. You can choose between those material that doesn't actually, they shouldn't release something. They should work at it is without collapsing, but you need to also consider in case it collapses in the body, what will happen. So you need to go and choose a combination that in case they release something, they don't have toxic effect on the body. But for your second question, you ask about biofuel, yes? I'm afraid that I don't also have a lot of information on biofuel, but I know that there are also works going on there.
And what about the, these enzymes, when we are talking about, so what will be the future and where especially in which organs or in which body part, it will be a playing role? Because as a physician, I'm a practicing doctor. So, it is very interesting phenomena that we are using some biochemical, these aspects for development and synthesis of enzymes. So where it will work in a good manner. What do you feel about this?
There is especially now a really long way until using them in the body. It's like maybe really in a fancy now. We are developing it. We are hoping in future we can do it, but there is still a long way. But definitely it's gonna be synthesizing something that our body cannot synthesize, like in molecular base. There are some in some diseases your body loses the function to produce something, and you can maybe add these enzymes in your body to replace them, and it is like a cure, but without using additional material. You use something that your body can produce it again. But still it is really a long way from here, but definitely using them is interesting because they are crystalline material. You can sometimes, if you are lucky, you can understand what is happening inside them. Like if you are doing a reaction, you can track how molecules behave inside that reaction, because you can see it via crystal X-rays.
Thank you for your wonderful explanation. Yes, definitely it is a future, because there are n number of diseases which we are not getting the answer. So enzyme may be the answer, because it is a chemical substance which will be working with the biology of the human body and really helping synthesis of certain enzyme, means certain functions can be produced by these enzymes. So this is a wonderful phenomenon what I feel, and that is the most active what we can introduce, because malignancy and diabetes and hypertension, these are the very important issues we are fighting, and we don't get much great answer as such, except the risk factors to control. So I think this is one of the very important thing. Robotic, robotics is also coming, introducing, but that will be a very much artificial, and how much it will work. It is like sending a spacecraft on a Mars. And whether it will land or it will not land, that is another question. That is a big question.
Yeah,
So I think that enzyme theory is really wonderful. Please work out on this. And if there is any latest news or some development is there, please let me know so we can introduce in our practices. Thank you. Thank you very much.
thank you so much for your comments. Definitely, thank you so much.
Thank you, Doctor Sir, with very perfect and useful discussion, guys, every day. Because mostly terms you have understood because you are from the medicinal field, and this is related to the health and medicine. Thank you, Lily,
Thank you
ma'am.
so much.
It's very best speech you have delivered here. In future also you'll be here for another speech as per your convenience of time. We are very happy, and all participants are having um, also the same remark as like me. Thank you to you.
Thank you so much. It was also really wonderful, wonderful for me to be in your presence, and I also enjoyed this discussion. Thank you so much.
Yeah, thank you. Yes, you can leave now. Okay, no problem.